So hello everyone, this is lecture 9 for thermal physics. In the last lecture we have completed the transport phenomena. So today the actual thermodynamics starts. So what we will study, let's see some content. So first we will introduce the thermodynamics, then expansivity, the compressibility we will study. Then we will go to the first law of thermodynamics. We will study what are sign conventions there, which we will use. Then the work done in various kinds of processes, the qualitative study we will see. Then the part dependence of the work done, adiabatic work done and its independence. Then general procedure for the work done means like isothermal process, adiabatic process, isobaric and isochoric. Then we will see some adiabatic relations means in two different methods like PV gamma constant, TV gamma minus 1 and the T gamma P1 minus gamma constant. So we will see all these relations. Then we will see the PV diagram and the various processes can be done on that. Then we will discuss the numerical problems. So this is the content we will study. So let's start. First, I need to introduce you with these terms, the intensive and the extensive parameters. So what are intensive parameters? These are those parameters which do not change with dimension of a system change. Means whether you increase the size or decrease the size, these parameters won't change. And the examples of intensive are temperature, pressure and chemical potentials, the Fermi energy, specific heats, isobaric expansivity, isothermal compressibility. Just remember these terms. I will explain you each and every term in detail later. And the electric field and the magnetic field, all are the intensive properties. Just like you can take an example of number density, means number density for a particular volume will remain constant and the volume can be increased, it will remain same because it's the ratio of number of particles per unit volume. So the ratio of two extensive quantities can also be intensive. That is, example is number density, because n is in extensive and v is extensive. So what are extensive? Extensive are those quantities which change when the dimension change. Means like number of particles can increase, box length can increase, area can increase, volume can increase, and the principal heat capacities can increase. So what is the difference between principal heat and the specific heat? So the principal heat capacities are those which is depending on the mass. Means larger the mass, larger will be the heat required to change to increase the temperature, and this is the per unit mass required is called the specific heat. So that's why the specific heat becomes the intensive and the principal heat remains the extensive. And see all the thermodynamic potentials we will discuss. The internal energy, the Helmholtz free energy and the enthalpy and the Gibbs free energy, all are extensive quantities, and these are also perfect differentials, means path independent. So you just need to remember these terms, that what are the examples of intensive and what are the examples of extensive. We will discuss all these terms in detail, so you don't need to confuse. Okay, so let's start with the expansivity and the compressibility. So before that, let me give you the physical meaning of change in volume, change in pressure and change in temperature. So see, these three quantities means they can vary. How they can vary? Means one thing can be remaining constant and other two can vary depending on each other. Means if you place the temperature constant and increase the pressure, then volume will decrease, and means then you can see that compressibility will be there. And if you see that pressure is constant and you increase the temperature, then volume will increase, then expansivity also will be there. So using the help of this thing, we can find two terms, that is expansivity and compressibility. So let's see what are these. So volume can be written as a function of temperature and pressure, means one can be remaining constant at one time. So let's define dV as del V by del T. With pressure constant, it will be dt, and del V by del B when temperature is constant, dP. So this can be written in this form. Now see that these two quantities will give us the different things. Means this will give us the expansivity, this will give us the compressibility, because with pressure volume decrease and with temperature volume increase. So these derivatives allow us to find a few important physical parameters like expansivity. First, it is isobaric, means pressure is constant. So we define the expansivity as this is the coefficient of expansivity. It is 1 upon V del V by del T. So you can see it as alpha delta T is equal to del V by V. So you just can remember in any form, you must remember this result, that is the point. Okay, and this is the expansivity for the coefficient, means with temperature volume is, so this is defined as the expansivity or the coefficient of expansivity, and this is valid for all gases, ideal or real. And now we can define it in terms of adiabatic expansivity also. What is the meaning of adiabatic? That means the heat exchange is zero, and if heat exchange is zero, then the entropy will be zero. So just don't confuse, we will discuss them. Just remember that if heat exchange is zero and the process is adiabatic, then entropy will remain constant. So that is the isentropic process. So alpha S will be given by 1 upon V del V by del T. So this is also expansivity, but at the constant entropy or the adiabatic. So this is the definition, basic definition. Remember this del V by del T, how the volume is changing with temperature and the per unit volume. So that's how you define this. Now see if this is your expansivity and at the constant pressure, and volume is changing with temperature, and if volume is changing with pressure, then it will decrease. That will define the compressibility. So this is your coefficient of compressibility, that is defined as minus 1 upon V del V by del V T. Means now this is changing and this volume is decreasing with pressure, so that's why we have put the negative sign outside. So this is the formula for compressibility at constant temperature. Now the 1 upon kT or reciprocal of 1 upon kT, the compressibility, will give you the elasticity or bulk modulus of elasticity. So remember, ET means that can be represented as bulk modulus B is equal to 1 upon kT always. So 1 upon kT will be minus V del P by del V at constant temperature. Now just forget these things. These are the cases for the ideal gas. Just remember this. This will be equal to this for any real gas or ideal gas. Now let's consider the ideal gas situation. So what happens to these results when the case is ideal gas? So let's see. For ideal gas, PV equal to nRT and V will be nRT by P. So let's find for the compressibility, we need to find del V by del P at constant temperature. So del V by del P will be given by, just take the differentiation with taking temperature constant, it will be nRT minus 1 upon P square. Now take the 1P outside, nRT by P, this is minus 1 upon P, and nRT over P is nothing but V again. So it is minus V upon P. So in place of now this del P by del V will become P upon V minus P upon V. So in place of del P by del V, just write minus P upon V. So V will cancel out and minus will become plus. So this bulk modulus will become P. So for the ideal gas, this bulk modulus will came out to be P, and KT is 1 upon B, so KT will be 1 upon P. So for ideal gas, KT will vary as this. So with V, P, KT will vary like this. This is the isothermal compressibility and it will become like this. So you must remember this for the ideal gas situation, that how the KT or the isothermal compressibility, why it is isothermal, because temperature is constant. So KT will vary like this for the isothermal. So must remember for the ideal case. Now let's see some other results also. Now this ET is nothing but the bulk modulus or the elasticity for the isothermal case. So that will be P, I defined this, so it will be equal to P for the ideal case, and this will be equal to B. Now for the expansivity, means this isobaric expansivity, we need to find del V by del T at constant pressure. So del V by del T at constant pressure will be given by nR by P. So because V is nothing but nRT by P, so del V by del T we need to find at constant pressure. So it will be T will become 1, so it will be nR by P. Now alpha P is 1 upon V del V by del T P, so it will be 1 upon V multiply this nR by P. Now PV is nothing but nRT, so nR will cancel out, alpha V will be 1 upon T. So for the ideal gas, the isobaric expansivity is represented in this form. So this will be the curve you will get. So remember this, very important results are there. Now to find the result for ideal gas for the adiabatic expansivity, we need to take some conditions for the adiabatic processes. So for adiabatic processes, you must remember this condition, we will see in detail. The TV gamma minus 1 equal to constant, where gamma is nothing but adiabatic index, that is Cp over Cv, and T is temperature, V is volume. So this will remain constant for the adiabatic process. From here T will be equal to C upon V gamma minus 1. From here we can find the del T by del V, that will be equal to C minus gamma minus 1. Simple differentiation this is. And from here del V by del T will be reciprocal as this, will be V gamma minus 1 V, C 1 minus gamma. Now this V will give you this thing here. Now from here you can see that V gamma minus 1 upon C, V gamma minus upon C is nothing but 1 upon T. So just substitute here, you will get V upon T 1 minus gamma. So this will be equal to this. So in place of this del V upon del T, we can just substitute this value, this one. So it will become this 1 upon T 1 minus gamma. So adiabatic expansivity will be equal to 1 upon T 1 minus gamma for the ideal gas. So these are the cases for the ideal gases. Now this is the expansivity. So for the compressibility, adiabatic compressibility, we need to take the reciprocal of this, that will be 1 upon Ks, means alpha S. Compressibility will be 1 upon alpha S will give you Ks. Ks will be reciprocal of this, means it will be minus V del T by del V. So actually expansivity defined for the increasing volume and with temperature, and the compressibility defined for decreasing volume with pressure. So adiabatic compressibility will be defined as minus 1 upon V del V by del P at constant S. Okay, so that's why this is compressibility, because volume is decreasing now. So the condition is PV gamma equal to constant. This is also a condition for adiabatic process. From here P equal to C upon V gamma. So now we can find the del P over del V because we know the P. So in the last we can just find del V over del P and substitute here. So it will be minus C gamma V minus gamma minus a simple differentiation there, and C upon V gamma, can we find it from here? That will be equal to P. So it will be this minus V upon gamma P, that will be equal to del V upon del P, because we will just take the reciprocal of this, will give you this. Now substitute this value here and you will get this result. This is the compressibility will be equal to 1 upon gamma P. So this is the adiabatic compressibility, and this is the compressibility. Then you can find the elasticity also for the adiabatic case, that will be 1 upon Ks, that will give you 1 upon Ks equal to gamma P. And also we know the isothermal compressibility is 1 upon P, and isothermal means bulk modulus is P simply. So we can just relate them. So Ks by Kt, this is V represented by kappa, so this is kappa, okay. So Kt by Ks equal to gamma P by P, that will give you gamma. So remember this result, very important. This is equal to adiabatic index, and adiabatic index is nothing but Cp by Cv, and this is equal to Es by Et. This is the elasticity for the adiabatic process, this elasticity for the isothermal process, and these are the compressibilities at the isothermal and the adiabatic. So must remember this result, very important result this is. So let's see some questions based on these results. For a gas under isothermal conditions, its pressure P varies with volume V as this. So pressure varying with volume this, B is proportional to. So we need to find the bulk modulus. So bulk modulus is nothing but 1 upon compressibility at isothermal compressibility, that is minus V del P over del Vt. So find the del P over del V. Cv, this is given. This is some constant. So del P over del V will be this. So just substitute this value here, and V is already there. So V1 minus 8 upon 3 will give you minus 5 upon 3. So bulk modulus will be proportional to minus 5 by 3. This will be your correct answer. Let's see one more question. For a certain system, pressure change with temperature as this. So this relation is given with temperature, where gamma is a constant independent of N, V and T. So gamma is independent of number and the volume and the temperature. We need to find the bulk modulus, and we need to find the isothermal compressibility. So what is the bulk modulus? Bulk modulus is again 1 upon compressibility. So compressibility is given by minus 1 upon V, del V by del P and constant temperature. So del V by del P. So let's find this. What is del P over del V at constant temperature? So see, this bulk modulus is 1 upon Kt, that's why we are getting this formula for the B, and this T is, P is depending on the temperature only, and T is constant here. So when this is constant, this complete value is constant, so del P over del V will be 0, and del P over del V will 0 means bulk modulus will be 0, and bulk modulus will be 0, and here isothermal compressibility will be 1 upon 0, so that will diverge, means tends to infinity. So this will be your answers for this. And now there is a very important result from the calculus we will use in the thermodynamics, that is reciprocity theorem. So what is this theorem? There are three variables x, y and z. So first we will take the derivative of x with respect to y with taking the z constant. That must be equal to taking the derivative of x with z, taking the third variable constant, multiply the del z by del y, taking the third variable constant x. So del x over del y, this will cancel out. So this formula you must remember, very important. So this is how this is defined. So this can be written as this. This is very valid result. So let's see how can we use this result. So there was question made on this. Which of the following relations hold true for alpha p, Kt and the pressure coefficients? So this is your expansivity, and this is the isobaric expansivity. This is your isothermal compressibility, and pressure coefficients hold true for alpha p and pressure coefficient. So which relation is hold true for this? So these are the four. So these four relations are given. So these are the relations between these three. So let's find the relation between alpha p and Kt just by finding the ratio alpha p upon Kt. So we know the formula for alpha p is 1 upon b del v by del tp, and for Kt it is minus 1 upon b del v upon del pt. Now see, this 1 upon v will cancel out, and it will become del p by del v with constant temperature above, and it will be del v by del tp. Now see, this is the same condition we are getting here for the reciprocity. This is x, this is y, and this is your some z, and these are your constants. So it will be del p over del t, and third variable is v, and this is positive. So this will be equal to this. Now this relation is hold for true for this alpha p upon Kt equal to del p over del t v. So this B option will be correct. Let's see one more question. Let delta be the coefficients of linear expansion defined as delta equal to 1 upon L, del L upon del T P, and alpha p be the volume expansivity defined as this. So we were discussing the volume expansivity actually. So this is represented by alpha, and they said that linear expansivity defined by delta. Then the correct relation which connects alpha p and delta is. So this is the complete volume expansion, this is the linear expansion. So how they relate? So these are the four options. So let's see. First, how we define the volume. To find the relation, we need to define the volume, that is Lx Ly Lz. So there is a cuboid type structure, so there will be volume will be Lx Ly Lz, 3 lengths. Now del V over del T at constant pressure will be equal to, derivative will be, first take this constant then find this derivative. So this will be like this, and take the derivatives of all three by taking the other two constants. So this will be del V by del T and P. So now see that we are assuming that cuboid have all the lengths same, means all three lengths are same, so V will be Lq. So in place of here, just multiply with 1 upon V to the whole equation. It will be 1 upon V and 1 upon L cube here, 1 upon L cube here, 1 upon L cube here, and this is R equal, so it will be L square by L cube, so it will give 1 upon L, here also 1 upon L, here also 1 upon L, and Lx Ly Lz are L, so it will be del L by del T at P. So this will become 1 upon L del L by del T in 3 times, and this is 1 upon V del V by del T P, and this is nothing but, this is your alpha and this is your delta, so alpha is nothing but equal to 3 delta. So these are the very important result you must remember, that this is equal to 3 delta. And if there was surface expansion, then this alpha will be equal to, means this surface expansion is defined by some gamma or the sigma, that will be equal to 2 delta. So for the volume it is 3 and for the surface it is 2. So that's why, because in the surface we have 2L and in the volume we have 3L. So that relations you must remember. So if sigma is your surface expansion, that will be equal to 2 delta. So that's it for today. In the next lecture we will start with first law of thermodynamics, and we will see how interesting it is. So thank you everyone.